I'm going to give a very quick introduction. I'm Professor Jill Adler from the University of Witwatersrand in South Africa, and it is my great pleasure again, because I had this pleasure yesterday, to introduce Professor Ferdinando Arzarello from the University of Turin. He's a Professor Emeritus, and I'm sure all of you were in the opening ceremony yesterday, and so know he was this year's recipient of the Felix Klein Award for a major contribution to development of mathematics education, research and practice over a career. And it is marvelous that we have this opportunity to listen to him this morning. Because of time, what we've just been discussing is Ferdinando will use the time between now and 11, because we're already nearly 10 minutes into the session, to give his talk. And then as it is tea time, those who would want to stay on to ask questions, please remain. And Ferdinando will remain here with you and take some questions and then be able to continue this into the tea time. So I thank you and invite Ferdinando to come and give his presentation.
Thank you, Jill, for your nice presentation. Good morning, everybody. Thank you for being here. And as you see, that's the title I give to my talk, going back to look forward, horizontal and vertical reflections on mathematics education. So, according to some scholars, mathematics education as a research field exhibits an horizontal knowledge structure, different from some more harder, let's say, harder scientific disciplines. It develops in two ways: within existing theories or languages, discourses, or with the creation of new theories, languages, discourses. As a result, agents from one theory, culture, may learn from the other, and vice versa. This is what the terminology I use, the knowledge structure of mathematics education, and then it's a sort of journey that I organize along this structure in the presentation, and it's my journey in it. So the rationale of this journey starts from classrooms, where we see that the processes happen: students, teachers, interactions, technology, also everything you think can happen in a class, have to be in a classroom. And it's a didactical principle, as Freudenthal wrote in his China lecture, this issue of processes. Processes are very complex. So what we are looking is, first, the question is what? What to observe? So it's the issue of research question. But once we have observed what, we can ask why. Which theoretical framework can be useful to answer such what questions? So the theoretical perspective is important there. After that, what we have is how to observe, how to interpret what we get using the theoretical perspective we have chosen. So this poses the question of the research methods. But that's not the end, because it's useless to know nice things without having concrete application. So the fourth question is hence. So the research design to elaborate in order to do something, to get something in the classroom. That's my frame, in a sense. And basing on my researchers in the years, and of course referring to a lot of other people who research in such fields, I will use example to give some answer. That answer I gave to such 4 questions, the why, what, etc. Because they can inspire fresh standpoints, critical reflections, useful for the improvement of mathematics education at large, and for the connections between research and the in-field practice with students and teachers. This will trace the red thread of my research journey. Here is the summary of what I'm trying to say today. First, 2 focuses on science and artifacts. Then some reflection and epistemological reflections of such things. And then idea of networking of theories, which realizes in a concrete way this issue of knowledge structure of mathematics education with which I started. So let me go to first section, science in mathematical discourses. You see there are some old people. I use only photos of people who are not still alive, but there are some things which are very active today from these people. And you see some books I used as an indicator of this. And the name to do before all is that of Peirce, which according to some people is that he made some epistemological import of perception. He observed that the mathematics has a paradoxical feature. Namely, it's purely deductive from the one side, and it's also an observational science from the other side. It's a sort of paradox. And it's an important promoter of new ideas. And the observational part, as well as the deductive part, are based on what he called diagrammatic reasoning, the issue of science with which we reason and on which we produce results in mathematics and also in teaching of mathematics. This issue is behind some new results, more recent than those of Peirce. For example, the processes of internalization of which are inspired by Vygotsky are there. And also the enlarged notion of semiotic system like that studied by Louis Radford. So, basing on that, I elaborated a notion, a construct, which I called the semiotic bundle, and I give you an example not example, I think it's very interesting because it gives an idea of what I mean with that, and illustrates the paradox of starting with Peirce. So the example concerns something which we can see on the screen of a computer. If I can, I don't see, here it is. And you can see this thing here, and the students, the first years of secondary school can see this, and we'll see how he's reacting to this thing. He didn't know already derivatives or things like that, but he knew some mathematics, of course, and you'll see a small video of this student, and you will see how he's interpreting these things. There is also the voice of the teacher who doesn't appear in the video. And let's hope that it works. It's in Italian, but there is some translation into English. The discourse is not so clear, but I ask you to check how you interpret what you see here. He's discussing exactly that. So it's a very difficult to interpret. It's something very confused is emerging. And it's, we could call the covariation between delta x and delta y. And I put some photo of what you have seen in the time order as they appear, but I interpret them going from one point to the other and putting the number of the photo I refer to. So the covariation you can see he is playing in 156 photo through his gestures and his utterances. So this issue of gesture is very important. He's interacting with the inscription, photo 1, 2, on the screen, and with the teacher. He refers to the teacher whose voice we have heard, and in photo 3 and 7. He makes us so explicit in a confused way that when bigger variation we have bigger variation of delta y, these correspond to small values of the delta x, and links this fact to the steepness of the tangent, see photo 4 and 7. The relationship between the resources he's using are revealed looking at these different registers, gestures, words, all things, inscriptions, etc. And it's a sort of a synchronic analysis we are doing. But there is also a diachronic analysis from time to check. For example, here you cannot know that, but we have followed this class in the years, and so from the past, the previous year, they had studied finite differences. The gesture he is using, this gesture here, come possibly from there. You see the photo on the right is from 1 year before when they were discussing the same student on the right. He is discussing the finite differences. And moreover, we have another interesting thing. This happened some minutes later. He comments, the teacher. I underline with the same color what he's saying and what he's gesturing. The teacher appears on the upside right side of the photo, and he says, let's say in this moment, if I understand properly, with a fixed delta x, which is a constant, and the student, also the other one, say, yes, it's joining some points, delta y, which is decreasing. What is happening here, I called a semiotic game. And in fact, the teacher, if you look, makes the same gesture of the student, but he doesn't use the same utterances. The verbal register changes. He's using a more mathematical way of saying things. So this is a sort of, we call, of game between different registers. With one register, the utterances, he says to the student he's on the right way, but in the same way, he uses the more technical words, suggesting him how to say such sort of things that he is understanding, in a sense. So this is something that happens very frequently in the classroom if one looks carefully to the processes that are there. So summarizing, this is what I call the semiotic bundle, which evolves in time, where you have the speech, the gestures, the inscription, the relationship between them. It changes in time. It could be something enter, more inscription can enter, more relationship, and so relationships. And so you can have an evolution of this, and you can use this diachronic analysis like to look at a movie, and a synchronic analysis, like to look at the photo of what is happening in the classroom. And we have sort of elaborated a tool to make such sort of observations. Remember of the questions I posed at the beginning, the how question, for example, and we call it a timeline. It is a tool to analyze the semiotic bundle, so we analyze looking at the things you see on the left, everything, utterance, gestures, inscription, etc. And from second to second, we make a careful analysis of what is happening. We can look to make an synchronic analysis, a diachronic analysis, etc. So this is like the tool, the storyboard of the movie. But behind the movie, there is something which is a theory. And that theory is what I've called the space of action, production, communication. So it's the tool, the model to analyze math processes, math teaching learning processes, looking at the embodiment and the semiotic cultural aspects. Now I show you another example where I underline an example of horizontal knowledge strategy integration, the one I started with. And so I have used, and other also colleagues have used this tool, the semiotic bundle, integrated with the blending by Fauconnier-Turner to an analysis of what happens in augmented reality environments. It was research coached by Osama Sweden in Ben Gurion University. We had a seminar in 2022, and we are now preparing some papers on it, and we have made careful analysis of this kind. I'll give you only some hint. The main idea is that in augmented reality, you can see, really, a function like that, and you as a student, and you have to accompany with your, to serve, we say, with your hand, this graph that you see in the air, and you see here the student who is doing that. He has the spectacles, the right spectacles to see what you don't see in the reality. And what he sees is also the tangent line that if he puts the hand in the right way. And what happens is that this movement of his hand produces also the green line. So, of course, as a mathematician, we see, oh, that's the derivative, etc. But the student doesn't know, and he grasps things, enters into things, into this, what is happening, through what we analyze as a blend. The derivative concept can be analyzed to the mental blend by Fauconnier-Turner. Here we have the function and the tangents, and they are put together in a blending, producing what we call a derivative. And that's something which can be grasped by the student, doing something and moving in this way. And here on the left, you see the type of functions that he analyzes. And what we have done is to elaborate a classification of gestures. Something are happening inside the AR environment, something are, but you are always there, and you are inside the augmented reality, but you also outside, and the gestures can be classified very clearly from these two start points. Some gestures are between the two, and this can help the researcher to observe the how problem, etc., and to solve some problems. So the knowledge structure of mathematics education can be improved in this way. So let me come to the second section, artifacts and mathematics. So artifacts were already in the two examples I show you, and artifacts have a long history in mathematics. Let's think to the tracers used by in the Greek culture to produce curves, what we call curves now, that solve a problem which could not be solved using, for example, the quadratic or the extension of two fields from the real. So that's from the rationals. So there is a long history behind this, which arrives to things like such augmented reality. So it's a history of a progressive cultural, cognitive, physical intertwining of artifacts with teacher and learner's actions. A person not so much interested in teaching, but interested in this progress, produced something very interesting, was Descartes. Descartes made evident, using the language of algebra, what can be done using suitable artifacts. You will see these tools there. Moving them in that way, you produce curves which can be described by the equations you see there, and he says this. So it's a step forward, important step forward, which connects two registers. The register which is from the Greece of the curves, and the register of algebra he had invented. Another step important was made by Seymour Papin not many years ago, in the 60s of the last century. He was producing, studying the body's syntonic interaction, students' artifacts, starting from Piaget, and his contribution, as he writes, is that he went from Piaget constructivism for his constructionism, and which was based in things like Turtle, Logo, namely objects, designing objects to think with, as the building bricks of the personal construction of knowledge. This is a further step that is behind the things we can see, can design, can use today in the classroom, artifacts that we can use in the artifacts. A third contribution, a very important contribution, was given by Pierre Rabardel, and is, as it's well known, is the instrumental genesis. And as Michel Arti pointed in his Klein lecture some years ago, he incorporated this tool with this construct has been incorporated into a diversity of different theoretical frameworks listed there. And what can be done, and we did, is that this instrumental genesis can be applied to the analysis of the dragging affordances, like activities allowed by many dynamic geometry software, starting from the old Cabri to the current GeoGebra and other things. And, but what he pointed out is also a deep connections of this instrumental genesis with activities in an economic and social environments. The use of tools is not concerned also only for classroom activity, but with everyday activities we have in different workplaces, etc. And he made a nice analysis of this. I think that fourth component that is current in these years is to go from the action-based embodied design to the functional, what have been called by people like Schwartz, Abramson, and others. You see there Alberto Becker, etc. The functional dynamic systems. So what is important here is that this approach points out that when a student and a teacher, students and teachers' sensory motor processes are coordinated in a common environment like those we have seen or we can imagine, something very important happens. And it's connected to this example of, now I'm not expert in baseball, but here is the outfinder or something like that they call. There is a system which is elaborated from there, which is it means that it's only something which is a unique system. The ball and the outfinder that tries to get the ball. And it's a regulation of the way he's running and the way he's moving, etc., etc. Something that happens when you are using an artifact. That's very important. It's the idea of functional dynamic system. That's something that is illuminating of what is happening in a classroom. By the way, one doesn't necessarily think only to digital artifacts for this. Every artifact. Also, the way we are using, interacting to open a door with something we don't know so well because it's not the same type of artifact we are usually using. So digital is important, but it's also physical artifacts which are on the stage. And I give you an example of this made in a research of ours. And in our research team, he wondered whether it was possible to introduce early forms of covariational reasoning already in the last years of primary school. Covariation is something typically connected to secondary school. So we have seen examples, 2 examples at least, I have mentioned today. But covariation is something which starts very early in the way young children reason, start to reason. And it's something very important because in many curricula, for example, in Italian curricula, but also in other curricula, the idea of having functions, relations, etc., are pointed by the curricula from the very first years of the school. And what we elaborated is a very simple thing, a tracer, like something similar in a sense, but much simpler than that of the card. Imagine that you can move the 2 bars, one on the horizontal, one on the vertical side, and you move that, but you have to follow this draw there. But there are 2 people. One is moving the bar horizontal, and the other is moving the vertical bar. And try to see what happens. And what happens is that these are early skills. What is used are early skills in grasping the covariation between the 2 varying quantities. And it's something that is conceptual, but also body syntonics, and it's mathematics in this sense. And so what happens is something that can go from instrumented covariation that we can see already in the secondary school, for example, using digital tools, to what we have called embodied instrumented covariation. And I tell something about this now. This embodied instrumented covariation can develop in students before any quantification. This is a new aspect that is not in the classical papers. For example, the persons who were more in this field are Thompson and Carlson, and they speak of when we have smooth images of change. But numbers are there. You think to covariation, every covariation you think at a certain level involves the covariation between numbers. But that's not yet necessary when you are looking at things from the very beginning, because you can have a first intuitive graduation of the speed. When you move that tracer and the 2 students are moving, I'll show you a video in a moment, they look at the speed quantity without necessity of having numbers. This is an intuition of speed as that described by Fishman. Fishman, in his book, wonderful book, Intuition and Science in Mathematics, says that to understand, to grasp speed, you don't need numbers. You need to observe, for example, to cross a road. You have to look at the way the cars are approaching, and you have to compare that car with the other car and to see if you can cross, you have to wait, etc. So here time is as an implicit variable, not yet quantified, but it's there, and it's the way you grasp. So the first types of tasks we gave to students are to follow such a sort of graph. So the first one, A, and what changes from A to B? They say, you'll see the movie in a moment, that the two students, while in the first case they can go on with the same speed, or whatever they call speed in their language, must change here because you have to go faster, and one have to go faster with respect to the other, and then they realize that when one line is parallel to the what we call the axis, one has to keep don't move. It doesn't move, and so they apply this thing, etc., etc., etc. I show now two very small short movies where you see these things, and moreover you see how there is another implicit things in the second movie, namely let's see some intuition of the steepness of what they are seeing. Let me.
Quindi in tutte e due le linee si muove sempre. Poi qua lui deve andare più veloce più piano.
That's the second. Oh, by the way, we are in the 5th grade of primary school here.
Sì, ma non c'entra, se la diagonale, se questo qua è un tratto, e poi c'è un tratto.
Please look at the boy with the red dress red. What he's doing, how he's moving his body to explain, to interact with others. It's very interesting.
Questo perché devi avanzare. Qualcosa un triangolo più lungo che più largo, la diagonale più ripica per stare qua, è tipo al contrario ed è più largo che lungo da una certa prospettiva, però tipo se ti metti qua e qua ci diventa tipo al contrario, scusate.
Okay, so this is embodied instrumented covariation, the first beginning of covariation. And to analyze what is happening here, we use at least three lenses, also thinking to the horizontal structure of math education knowledge. So the growth point theory of McNeil, I have not the time to enter into it. When you start with a gesture which is important to reveal what you are grasping, and the gesture is repeated. This is a catchment, and the growth point is the starting point for that. The initial sequence of catchment produced by students marks the birth of this embodied instrumented covariation. Moreover, we have Hofstadter-Halibali's gestural simulated action. There is an imagistic component in gesture that makes it possible for students to rethink and reproduce offline. So you are using gesture online, but you can repeat things offline. And that you are thinking. And these are gestural simulated action. And so they rethink and reproduce offline their interaction with the artifact and elaborate it in an early covariation form. And of course, we have also the body artifact, the functional system. It allows to scrutinize the early genesis of covariation through students' interaction with an artifact aimed to foster covariational non-numerical reasoning. We are looking forward, I skipped this part, using a duo of artifacts, taking ideas from other people's works, when you are using a digital and a physical instrument which are doing the same thing. And what is happening is that the way ideas and understanding is produced is different in the two cases. And this is realized by the students who are using the two. I skip this, but I read only a comment of a participant. You can read it. When moving the bars with the finger, follow the point because the concentration went on the eye, which followed the movements on the screen, while the physical tracer, with the physical tracer, the hands moving the notes, remain bound to move along the two guides. The other artifact, the digital one, you have to use digits to move the points. And so this is the enrichment given by this thing to the knowledge structure of mathematical education. Now let me come to some reflection, epistemological reflection. And we have seen how our artifacts can, using the words of Schoenfeld, blur the boundaries between formal and informal mathematics. And I will discuss now, I will enter in this thing here, to reflect on what I call the double gap in processes of teaching, learning, proof. This double gap has epistemological and cognitive features. The epistemological one concerns what is empirical perceived as true, using the artifact, etc., and what is logically valid within a suitable theoretical framework, which is the framework of mathematics. And also there is a cognitive aspect. Between the first arguing phase, where I think to the student, the first movie, he was arguing, but in a very unordered way. And there is this gap between this arguing phase and the proving phase. So what we elaborated with this is the gamification process produced to some tools, the logic of inquiry, the abduction, and the result was gamification. I have not now the time, because time is running, to enter into much in these things. I show you the example concerning gamification. Behind it there is what I say only is the logic of inquiry, discovered by Hintika. He's mentioning Sherlock Holmes using this logic of inquiry, in the logic of questions and answers, and he put forward a deep link with game theory. When you are reasoning in a chess game, when you are playing a chess game, you are, of course, classical logic is there, if this, then that, but you are looking, in a sense, in a reverse way to the result. And this is the logic of inquiry, which has been elaborated by Hintika in a very nice way. And what is happening are the production of abduction in the sense of Peirce. You see his famous example of the bag of beans. And in digital environment, and particularly in practices concerning the geometry for example, in Cabri, in GeoGebra, and such sort of things, we have the production of a lot of abductions, which are in a sense the opposite, the reverse way to deductions. And, and they are a result of this embodied approach. Abduction, particularly, we have what we see is the production of manipulative abductions, namely the, I quote only from Magnani, manipulative abduction happen, are abduction, but that happen when thinking, when you are thinking through doing, and not only about doing. I'm doing with something in that moment. Then I can reflect and do something. This is the thing that can be shown in this example, where is a type of game you are giving to students. This is a very simple geometrical game. Now we are using this approach also for more elaborated mathematical things like limits and continuity, etc. And it's using the technology concerning robust and soft construction. In a robust way, you have there built in GeoGebra E as a middle point of DB, F a middle point of AC, G intersection BD and AC. These are robust. They are all, if you drag, they are always have this property. But the quadrilateral A, B, C, D is generic, is soft. You can move without any problem. That's a contrast. And you have two students. One is the verifier, and he can move the point C, and one is the falsifier, because in the logic of induction you have this way of game. The gaming is between someone who tries to win the game and the other one who's opposite to this, verifier and falsifier. So the verifier goal has to make EF and G coincide, while the falsifier goal is to prevent the verifier from achieving the goal. And so each game consists in two moves, the first by the falsifier, the second from the verifier. I show you an example how the player wins when the player who achieves the goal. For example, here, let me go to the second example. Okay, this one. Here is the move of the falsifier. It produces very strange quadrilateral. This is an interesting thing that happens in such sort of things. And, okay, sorry. And this is what the verifier does. Oh, you can try to make me difficult things, I'll do that. And so the verifier wins. So what is happening here, I have not the time to enter into details, there is a challenge which is focused on conceptual aspect, and there is a functional interpretation of mathematical sentences, which is not generally there at the beginning, but the gamification makes them there. So if for all D there is a C, so G, E, F are the same. This is the functional interpretation which is produced, can produce such a task, starting from the facts observed during the game, formulate geometric conjectures based on the game and express in the form if, then. And so behind this there is the theorem that the quadrilateral is a parallelogram if and only if diagonals put each other in the middle. So that's, and we have seen that during such games, often we see the production of non-prototypical figures. There is an enrichment of the example space so critical in producing solutions. So this is made on the robust soft construction in digit A. I have not the time to enter in the details of Gibson and Abramson references, but I underlined that this add another component to our knowledge structure of mathematics education. We have produced all these examples, and I reflect on this we can reflect on this using the networking of theories. I am very happy to have participated to the elaboration of this approach to mathematics, networking of theories. By the way, 3 Klein medals are in the group of networking of theories. That is, you can see them there. There is Michel Artigue, Tommy Dreyfus, and myself, and many other people there. One of the beginning, on the first meetings of the network networking theories. So the networking offers a concrete way to realize the horizon of theories put forward by Bernstein and which accompanied my travel in all this thing. I have not the time to enter into because it's almost at the end, and I skip this. I skip also the examples. Covariation is always in this example. I show you only something about this second example, where there is what is there is the use of the way of Galileo experiment of the rolling of a ball, and we have interpreted what happened in the classroom using a digital tool, also a discussion, etc., using two lenses, the semiotic bundle and the Toulmin model. And what we have realized, this has produced some papers also, to which participate many people, from whom also Angelika Bickner, it produced a more comprehensive understanding of the teacher support in the course of the lesson. I have made some explanation of this, but I skip because of time. And it was using two tools, and what was the conclusion is that using one framework makes the sequentiality and the relationship visible in which the different levels of covariational reasoning occur. The teacher is stressing this aspect, and then it's there in the way things are happening and are revealed by the framework of semiotic bundle. While the other framework, so the Toulmin model of analysis of argumentations in the classroom, it's on the backstage and underlines the fact that the teacher is also attentive to this sort of thing. So the aim is to produce understanding of covariation in students, but he's also attentive, he's also considering and using the issue of argumentation. So what is happening in these two frames is that they can produce a different interpretation of the same phenomena and, can change the status of this phenomena. Every thought, when coming towards the other, questions itself about its own unthought, said François Julien in one of his papers. So what I'm concluding is that the knowledge structure of mathematics education is a very rich field to investigate and approaching it with our four main questions. What we have seen has been something connected with science in mathematical discourses, artifacts in mathematics, the connections between them, and we have reflected through epistemological lenses and with the networking of theories among this. And so what has been realized is that, that if you want to understand objects, you will want to understand the network of relationships they enjoy with all the other objects of their species. And that's what we are doing in math education. This is a quotation for Barry Mesul, who is speaking, who is an expert in category theory, and is speaking of the Yoneda effect, where you have this thing in strict mathematical two topics. This Yoneda effect is, in fact, happening very frequently also in our field of mathematics education. And I have tried to illustrate this effect in my presentation with the semiotic bundle, the epistemic game, the physical and digital artifacts, and with the networking of theories. These things represent some stages of my research journey following an ideal thread towards understanding the teaching-learning processes of mathematics, but also producing, because it's very important to produce field practice with students and teachers. These are, I have not spoken of these. These are things produced with teachers in Italy. They are books generally or other things produced in Italy. But what personally I enjoyed much was going in search of this red thread with so many inspires and friends over these years. I represented some of them, particularly the students, for all of this. And I thank them for all this. And I thank you all for your kind attention. Thank you.
Thank you, Frederick. It's very bright. We can't really see. We do have a few minutes. I don't know if you could switch the lights off. Is it possible? Whoever's managing the lighting? If not, then perhaps those that want to ask and engage with Ferdinando, if I can ask you to come forward, and then we can stand here.
Okay.
And we can play something. Can you hear us? Yeah. Are there any questions?
It's a very good talk.
Thank you.
Thank you.
I'm interested with that game thing.
Yeah, we don't have a mic, I'm afraid. Can you talk up?
That game thing. There's a kid will play kid.
Oh, there we go.
Okay.
I'm interested in that game that you show in the video. Can I find information where I can make it?
You mean the video about
The boy play with the...
with the tracer?
Yeah.
Yes. And
I want to make one.
yeah, they had seen this. I don't grasp what you mean.
Do you have information how I make one?
How do you make it?
How do I make it?
How to make it so?
The game.
How to do the tracer. We made that.
I know, so where can I find information to make one?
And so it's very, particularly we use the fathers of some researchers to do that. You do
lost.
another thing. No, this one may be another thing. Yeah, why not? Yes.
Can I suggest you email Ferdinando and ask him to send you information about how you make it?
Okay.
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 How is it constructed?
Yeah, okay.
Yeah.
It's a very simple thing, you see. It seems simple, at
It
least.
looks simple, but maybe you need some help.
Oh, sure. But fathers are very useful, fathers of researchers, in this case, are very useful because they have that, there is a song from an Italian singer, Conte, who speaks of the intelligence of people working in electricity. And I think that this intelligence is very important in such sort of things. It's that sort of thing that is not so sophisticated. It doesn't appear so sophisticated, but it is. And it's something that we can look at when we are in a classroom interacting with the students, because it's there that there is some understanding and grasping of concepts sometimes.
Any other questions? There we go.
Oh, please.
Thank you very much. That was really very, very interesting to sort of hear all your work summarised so in such a connected way. I was really interested in the co-variation idea and you mentioned a dynamicity of coordinated embodied movements. Would you see this in the way children are moving together in a space?
Yeah.
Watching each other, pausing and then aligning as they move in coordinated ways. Again, themselves as little objects interacting with other objects.
Yeah.
Would that be sort of in that category of covariation?
Yeah, I think that you mentioned a very interesting issue. We have tried to explore something connected possibly with the issue of augmented reality. But because augmented reality, you have this thing that is with 3 dimensions, but it's something that you go from 2 to 3 dimensions and back, and that could be an interesting issue to analyze. But unfortunately, we have not yet done that. I think it's very inspiring. Thank you for the inspiration.
Thank you very much. I might email you and question you further. Thank you.
Yes, a question. Here you go.
There.
Thank you so much. I appreciate the way you go deep into the ocean of theories in mathematics education, and you showed up how much there are a lot of theories. That's very interesting. And I saw you extending one theory from the other theory, extending from one theory to the other theory. That's very interesting. And my question maybe is, you focused on horizontal knowledge structure, but if you make it extension of a theory, and I think the one important point in mathematics education is, what about the vertical knowledge structure?
Yes, I understand.
So kind of layer and layer and layer.
Yeah.
So can you categorize that into layers and to go to the vertical knowledge structure? Thank you.
Thank you. To clarify, I use the Bernstein framework, where he is a very well-known framework in pedagogy and in learning sciences. And it marks, maybe a bit exaggerating, but the difference between horizontal, but he says it contains also this, so to say, vertical. But for him, the vertical, and that sense I use the term for Bernstein, the vertical is typical of, for example, science like physics. In physics, when you have a result, what was before, of course you have still, but it is destroyed in a sense, but what you have found in the last result. For example, of course, you can, when you have the Galileo relativity, you don't use any longer the Aristotelian approach to movement, etc., because it's not, it's wrong. So vertical means that you add things that, in a sense, destroys what was before. Of course, you can reflect that, of course, now we have the relativity environment of Einstein, or the quantum environment. It has destroyed, but in a sense, so we are using the Galilei approach in everyday science, etc. So there is something horizontal in that. But what is stressed in the approach of Bernstein is that in our approach of educational science, it is not so destroying. The idea is not to destroy what was before, but to enlarge, to enhance thing in order to understand better what you had before. In this sense, is horizontal. And in this sense, it has been interpreted by one of our researchers, Lerman, in his book, in his paper, in the book produced in Hamburg for the early career research students, underlines this and uses that framework also. So in this sense, one must be careful using words. So I use that because it is very well known generally, but it raises interesting questions as yours, and I agree with you that in fact, if you look in the title, I use also the vertical world, not only the horizontal world. And I think that it's there in this sense, not in the Bernstein sense, so strong against what happened before in empirical science.
Perhaps then you can join me in thanking Ferdinando for sharing his journey with us in such an eloquent way.
Thank you.
And giving everybody here some insight into what it means to have a 40-year journey.